This is another constant volume process. The water in this tank, the steam in this tank is cooling down, and we are supposed to find the heat loss and entropy generation. Let's throw in also, let's find the final pressure as it cools down. So just so that we understand what's going on, let's draw the process on a TS diagram very quickly. And of course, we are going to use PC model. Initially, this 100 kPa is the pressure. So we know that the initial state is somewhere along this line, along this 100 kPa line. So we have no clue. Only thing else is given is mass and volume, the mass of the water and volume of the tank. So let's go figure out state 1 first, and then we'll look for state 2. So we notice that the information that is known about state 1, I think we have to continue it in the next page. So let's start here because there is simply too much to do about state 1. So what is given is pressure equals 100 kPa and volume is given, which is, the volume is given is 10 meter cube and 20 kg. Mass is 20 kg. So therefore, we know a second thermodynamic property, specific volume becomes 10 by 20, 0.5 meter cube per kg. So immediately we know that state 1, pressure and specific volume is known. So we have done this in chapter 3. If you go back there, if you forgot, we got to immediately find the Vf and Vg. And if V is in between, then we'll know it's a mixture. If V is more than Vg, it's a superheated vapor. And if V is less than V is less than Vf, then it will be subcooled liquid. So Vf and Vg, how do you go about finding that? So therefore, Vf would be Vf at 100 kPa and Vg at 100 kPa. So to find that, we go to the property tables, and because pressure is known, we go to the saturation pressure table and look for the 100 kPa line, which is 0.1. So we can pick up Vf and Vg. And again, I have already done that, and you must have already had enough practice on that. So I'm just going to write down the numbers here without the units. V will be something like that, Vg, and Vg will be 1.69. Obviously, we have a phase change fluid because can you see that is 0.5. So therefore, V, which is 1 minus x times Vf plus x times Vg, is a weighted average of Vf and Vg. Now we know Vf, we know Vg, and we know V. Once we substitute, one equations, one unknown, and this produces the quality x to be 0.29. So now that we know the quality, we know we might need U and S because energy and entropy equation contains those. So let's be proactive about it. We know what is U for this mixture is going to be 1 minus x times UF plus x times UG. Again, I've already picked up the numbers. 1 minus 0.29. UF is 417 and 0.29 UG is 2506. So therefore U become 1033 kilojoule per kg. Similarly, entropy is 1 minus 0.29 and SF is 1.30 and SG is 7.36. So we get an entropy of state 1 to be 3.09. So you can go and check. I mean, see entropy 1.3 and 7.36 come from basically 1.3 and 7.36 coming from here, U F in UG, VF in VG, and this is the pressure is 100 kPa. So that's pretty straightforward. Now let's go look at state 2, what we know. So for state 2, again, we'll do the same sort of thing. It cools down to a certain temperature. Of course, the specific volume will remain the same. The first thing to notice is that this is not going to change because the mass of H2O in the tank cannot change because the tank is cooling down. And the volume cannot change because it's a rigid tank. So we know the temperature, which is same as the surrounding temperature. I think the surrounding temperature is given in this problem, as you can see, 30 degrees Celsius, whereas this thing is cooling down from 100 kPa, sorry, about 100 degrees Celsius, because it's 100 kPa, we know this temperature is 100 degrees Celsius, and this is our state, right? We found state 1 to be here. State 1 is here because, why? The quality was calculated to be 0. Let me take the red color. This is my state 1. So where would be the state 2? Let's think ahead. State 2 would be at 30 degrees Celsius, no matter what. That's given to us, right? Somewhere on this line. So to find the state, we know the specific volume. So again, we'll find the F and G state. But this time, the F and G states are not at 100 kPa, at 30 degrees Celsius. So to find VF and VG at 30 degrees Celsius, VF at 30 degrees Celsius, VG at 30 degrees Celsius, we'll go to the temperature saturation table, pick these numbers up, and you'll find it is basically, this is practically 0.001, and VG is about 32.9, and that gives us V equals 1 minus X VF, the same formula, but this time VF and VG are different, they're known, and V is same, 0.5, and you can show that X is given as 0.015. So therefore, if you go and try to draw your state, obviously the quality is very low, so this will be our state 2. So notice, immediately you can see the pressure will be so much lower here. Can you understand that? Because the pressure line here is something like this. So what will be the pressure? The pressure will be the saturation pressure at 30 degrees Celsius. So we can immediately find pressure. The final pressure would be P must be P set at 30 degrees Celsius. So if you go back to the saturation table for temperature saturation table, at 30 degrees Celsius, the pressure is only 4.25. Can we see that? So the pressure is 4.25 kPa. So imagine atmospheric pressure is 100 kPa. The tank is almost vacuum. So unless it's made out of really thick steel, the tank is going to collapse. And what we did, we just left the tank overnight, just to cool down. So this is the power of atmospheric pressure. Anyway, so now that we know the pressure, we don't really, in this particular problem, we need to find U and S. So U would be, again, 1 minus X times UF plus X times UG. Again, this is 1 minus 0.015. UF is 126 plus 0.015 times UG, you'll find to be 2416. So that gives us a U of 160, whatever the unit. Similarly, S is 1 minus X SF plus X times SG, which is 1 minus 0. which is 1 minus 0.015 times SF, which is again from the saturation table for water, temperature saturation table. SF turns out to be 0.4369. And sorry about that, plus 0.015 times Sg, which is 8.45. And if you do the math, entropy turns out to be about 0.56. Okay, so now that we know entropy and internal energy for both the states, the real analysis, the closed process analysis, will tell us delta E equals Q minus W external. Again, it's a constant volume problem. There is no external work. And if we neglect kinetic and potential energy, Q becomes delta U, which is mass times U2 minus U1. So that's really simple. The mass is already known, and we found U2 to be 160 and U1 to be 1033, and that gives us negative 17460 kilojoule. So the negative sign tells us that the heat transfer is negative, means heat is lost. So if the question is find the heat transfer, the answer will be negative this. But if somebody says how much heat is lost, Q lost, the answer should be positive, right? Because here the sign when heat is telling us which way the heat is going. Heat in is positive, so negative means heat out, which will be negative. So heat out, Q lost, Q out, etc. will be positive number. Finally, to get the entropy generation of the universe because of this constant volume process, we must take a boundary which goes around the system that includes the immediate surrounding. So we know the temperature of the boundary now will be 30 degrees Celsius, which is 273 plus 30, 303 Kelvin. And heat is passing through this, entropy is coming out of here. So if we write the entropy equation now, delta S is this, therefore Sgen universe is given as delta S minus Q over TB, which is mass time S2 minus S1 minus Q. Notice Q is 1746 negative this divided by 303, and we have found S1, S2 and M. If you substitute them here, you'll get an Sgen of 6.97 kilojoule per Kelvin. So let's go quickly verify this solution using a test calc. You'll see how fast you can do that. So to launch the test calc again, it will be a closed process. So if we follow the system, closed, and generic branch, it's a uniform system. What uniform system means is that at a given time, we have only one state describing the system. And it's a PC model. And then finally to launch, we click here. Okay, so state 1, what is given is 100 kPa, and mass is 10 kg, and volume is 20 meter cube. So that will produce the, oops, I think I just made a mistake. Volume was 10 meter cube, I believe, and mass is 20 kg. And that's why V was 0.5, and notice quality has been found. And of course, we can draw a TS diagram to show exactly where the state is. So if you go to state 2, what is known? Okay, we can just write down what is known about the problem. Mass must be the same. Volume must be the same, rigid tank. And the only other information that is known is that temperature became 30 degrees Celsius. We found both the states. If you do a TS diagram, you can see the states there. 1 and 2, and notice this, the specific volume remains constant. So if I click here, constant volume line, 1 and 2 must be along this line. So a test verification not only gets your number correct, but you get a better concept that you didn't make any conceptual mistakes. State 1 and 2 have the same specific volume, and on a TS diagram, that's how it looks. So now that we know state 1 and 2, we go to the process panel and load the states 1 and 2. We also know the other kind of work, which is the sum of shaft and electrical work. In this case is 0. There is no other work transfer. And the boundary temperature is 303 Kelvin. So now if I calculate, we found the heat transfer and we also found the entropy generation. It's 7, which is very close to our manual answer. So the problem is solved and verified.